Okay, thanks Alicia for that introduction, and thanks to everyone for joining today. I know it's tough for some people, it'll be tough to listen to 40 minutes, 45 minutes about wastewater treatment, so I'll do my best to keep it interesting. And first of all, I'd say before I start that there's loads of colleagues who are listed or mentioned in the slides. I won't mention some that I probably haven't even listed in the slides, so I'm going to start by thanking all of those first, because a lot of the projects that I discuss or that I run through, you know, it's not just me working on them, it's lots of other colleagues as well. So I just want to get that out of the way because there's been so many people who have helped with a lot of these projects over the years. So to start off, yes, as Alicia said, I'm originally from Limerick and went to primary school and secondary school in Prof in County Limerick. And from there, to be honest, I didn't really like school very much, and I got into a bit of trouble there, but I loved reading. I was very lucky my parents had the Word Book encyclopedias lodged in my room, and my mum reminded me recently that apparently I read them cover to cover, and that's what I used to do in my spare time. But actually a great thing about that was it just gave, about having those types of books available to you, was it gave me such a really good background in so many different areas, everything from history to art to science, engineering, etc. So I think from an early age I was interested and curious in lots of different things. And obviously I started cycling at an early age as well, constructing some civil engineering ramps, and often landing on my head or my back trying to get over them. And that's, I suppose, something I was into from a very early age. All right, brilliant.
Good, yeah.
Yeah?
Yeah.
Okay. So, just skipping on ahead, I graduated actually in environmental engineering. My BE was environmental engineering. Kind of skipped through different engineering disciplines on my way through 4 years of engineering. And graduated with a degree in environmental engineering in 2002. Actually, my final year thesis was in structural engineering, so anyone here who's from a structures background will be happy to hear that. And actually, I almost did my PhD with Annette Hart in structural engineering through an Irish Research Council grant, which we were awarded, but decided in the end to do a PhD in wastewater treatment, as you'll see in a minute. So some of my other colleagues here, of course, I had lots of different lectures over the years, but I've just listed some of my colleagues who have been working, who I worked with recently, including Professor Paul McDonough, who would have been the head of civil engineering at the time. And both as head of civil engineering when I was a student, when we were all afraid of him, but then when I was a colleague later on, I found to be an excellent colleague and someone who influenced me a lot in my career. Professor Mike Hartnett and Dr. Brian McCabe are also two colleagues who have worked with me, who taught me as a student, but have also worked with me over the years. And I still actually, to some extent, regret not doing a PhD in structures because it's an area I'm quite interested in anyway. I did my PhD here in wastewater treatment, so the wastewater treatment lab was based in what is now the Eoghan Theatre, which is kind of a fascinating building. It was built in the 1980s, and it was a bleach and flax mill, became a warehouse, then a munitions factory, believe it or not. And then it was taken over by Irish Metal Industries, and there was a brewery there at some stage as well. So from that it became a soil and wastewater research building, and it was damaged by fire in 2008, which was in the middle of my and other people's PhDs, which was not ideal, given there was no cloud servers, all our PCs were burnt, all our lab books, everything completely went up in smoke during the PhD, so that was an interesting time. Luckily, unluckily for us, but maybe luckily for the building, most of the damage was to porta-cabin offices and some of the laboratories there, but the main structure wasn't damaged, and it's now actually was converted into what's a beautiful building, the O'Donoghue Theatre. So after all that, I did get out and finished my PhD in 2010. It was in the area of wastewater treatment, and it was looking at, I suppose, low technology methods of treating wastewater, with a heavy focus on developing new mathematical models to describe the type of hydraulic and hydrodynamic and biochemical reactions that occur in wastewater treatment systems. These are some of my colleagues, some who work with me now, who were researchers or lecturers at the time while I was doing my PhD. And Ted O'Reilly, a good friend of mine and good colleague, did his PhD at the same time as me. I should also mention Rafa Urban, who worked with us for a couple of years. He was a really brilliant, one of the most brilliant people I ever worked with, postdoctoral researcher from Wrocław in Poland. Unfortunately, he was tragically killed in a car accident a number of years ago, and he would have been just in his mid-40s at the time. But he was a huge influence on me in terms of the mathematical modelling that I would have done. My supervisor, I'm just going to put on the presenter, was Michael Rogers, and if I had all night I could talk so much about him. He had a huge influence on my career. He was a really brilliant supervisor, really pushed us hard, was someone who, taught us a lot about how to write properly, didn't accept us coming in with, badly written documents. Very quickly knew you had to be prepared for your meetings, and you had to know your stuff. And in some ways it might be considered tough, but actually he was a huge influence to me, and I'm forever grateful for the supervision, for working with him over the years. And I'd also like to mention John McQueen, who worked with us in the lab, had a long research career with Michael, and was also a brilliant person. So I was really lucky in this group. He died a number of years ago, but was a soil scientist with a vast international career. Okay, so I'm kind of skipping ahead a few years to, I suppose, university life, and I've skipped a few years in between there, but I suppose why water, wastewater and sanitation, why is it an area of interest? I mean, to be honest, all engineering is of interest to me, but currently as of 2022, which is I suppose the most recent data, there's just over 2.2 billion people who don't have safely managed water. Far more people have access to mobile phones and the internet than have access to clean water, which is astonishing. And 3.5 billion people lack safely managed sanitation around the world. And it's not just in developing countries, it's in developed countries as well. And it's the leading cause of death for children under the age of 5, and the leading cause of malnutrition for children under the age of 5, lack of sanitation facilities. So for me, it's always been an area of interest to me, and even in developed countries, there are significant problems with water and wastewater treatment, problems such as the costs of maintaining the infrastructure, the energy consumption that goes with trying to treat wastewater and treat water, which I think a lot of society are not really aware of. The types of contaminants that have to be removed, so basically everything that goes down the sink and down the toilet has to be somehow taken out of the wastewater treatment plant. That includes cosmetics, pharmaceuticals, all the other products that end up in the system. Wastewater infrastructure is now challenged by climate. Additional rainfall gets into the wastewater treatment plants, which could have significant impacts, and there's lots of other areas. And across Europe, which is obviously a very developed region, you can see here, this diagram just shows the areas of Europe that have good, moderate or poor water quality in their surface waters. Basically, if you saw any green there, it would indicate that we had excellent water status, and you don't see any green. And if you see red, it means that water quality of surface waters is considered very poor in those areas. So that's within the EU, and you can imagine in other areas there's equal amounts of stress. I was quite lucky. The head of Eoghan did me a favour last week by coming out with a pretty bold statement to say that the system in Ireland is in a desperate state. I don't know if anyone read that, but it was, for the head of Eoghan Irish Water to come out and say that, and it was pretty critical, I felt, of the government in terms of their approach, and maybe of society in general, to water infrastructure. So it was quite lucky for me to have this presentation, but I can see why they might think that. So that's kind of the context. The two areas that I'm going to focus on with a few detours along the way are the area of aeration and process control. I'll describe very briefly, and I'm not going to go into technical detail in this talk about those two areas, but they're the two kind of, I suppose, core themes that our research has focused on over the last number of years. So aeration, it's quite a simple thing actually. In order to drive wastewater treatment, we need to get air into the water. The air enables the bacteria that we use for wastewater treatment to carry out various reactions, and so those reactions are what we use to actually remove a lot of the contaminants from wastewater. So it's really the key driver in wastewater treatment, but it's also the key energy consumer. and it's the key component that we use to try and control how well the treatment process works. There's different technologies that we can use, technologies such as surface aeration. It's nice engineering technology, I think, because it's really simple. It just comprises of sloshing the water around the place to create turbulence, and that helps air get in. It's very robust, actually, quite inefficient, but very robust, doesn't break down. And then we have, I suppose, relatively, well, more modern over the last few decades, we have diffuser-based systems which blow air into little diffusers, which are located at the bottom of wastewater tanks. And these create bubbles, and these bubbles dissolve into the, well, they're supposed to dissolve into wastewater, but about 70 or 80% of all the oxygen we blow in actually just comes back out into the atmosphere again. And maintenance in these is a major problem, because if you can imagine, most people haven't seen a wastewater treatment plant, but a tank would easily be the size of this room, the volume of this room, or multiples of that. If you have these diffusers on the floor, which they will be on the bottom of the tank, and they start getting clogged, how do you maintain them? What do you do with the millions and millions of litres of wastewater that are already in the tank? And there's wastewater coming into the system all the time, you just can't tell the city to stop producing wastewater. So the maintenance of these devices is a major problem. And the other problem that we try and tackle is there's this kind of performance gap. So these technologies work very well when they're applied to clean water, but because of different chemicals, including our household detergents that we put into wastewater, it actually means that these technologies tend to perform very poorly, or a lot more poorly, I suppose, than they otherwise would in wastewater when compared to clean water. So that makes them less efficient, causes us to spend more money on aeration and other issues. So that's kind of the first area of aeration. The second bit is in process control. So this is how do we control the overall wastewater treatment process so that we meet the discharge limit. So every wastewater treatment plant has to meet a discharge limit, a regulatory limit, which in Ireland is monitored by the Environmental Protection Agency. It has to be as efficient cost-wise as possible, because while Irish Water are complaining they don't have enough money, so is every utility around the world, so they have to try and drive down costs. These types of control systems can try and reduce or predict maintenance so that the plant doesn't break down, that we can have maintenance before a system breaks down completely. It can be used to try and increase system capacity within the same volume or the same infrastructure footprint. And later, as we see, we can use process control to try and reduce the emissions, so gaseous emissions that come from treatment plants. So these are kind of the two main areas that I'm going to run through, and as I said, we'll have some detours in other research projects along the way. Okay, so the starting point in my work, as I mentioned, was my PhD, and it was the development of this system called a horizontal flow biofilm reactor. So I developed it in the lab, did some side trials. When we developed a patent on it, and one of the nice phrases that I learned here was busterfidonic, which is this type of flow in a particular unit. I'd never heard of that word before, but it fit nicely into our patent, and it was actually one of the two things that allowed us to get a patent was to use that word, which I know is crazy, but when you get into patenting, you kind of see that really small things make a big difference in patenting. So we developed this technology, and why did we develop it? Well, the first thing was that the way we delivered air in this technology was passively. We didn't force it in using any mechanical mechanism. We did some little tricks with hydraulic flow, with how the wastewater flowed through the system, and that enabled air just to basically be driven in naturally. Okay, so there's no mechanical parts to aerate this technology. It required a pump, but we also set up systems that required no electricity as well, using basic tipping buckets. The systems were very little maintenance. If you basically don't have any electrical or mechanical parts, then there's very little that can go wrong with systems like this. And we could use it to remove nitrogen, which is just a contaminant which is very tricky to remove. And one of the nice selling points of this technology was that it might cost in running costs between 0 and 20 euros per year, depending on the topography of your own site. Of course, like every technology, it had disadvantages, such as the cost of plastics, manufacturability, because of the way we had arranged the sheets in it, and it was only useful for very small scale technologies only. So we did commercialize the technology. It had some success, but the cost issues at commercial scale were a problem for it. But it was actually a great technology for teaching in wastewater, and we were able to do some really nice PhD work using the same system to treat gaseous emissions from wastewater treatment systems as well. And I just mentioned Colin Kennelly and Sean Garrett, who did PhDs in that area. So that was kind of the starting point that came out of my PhD, which we worked on after I started working here. So the next bit, and I should state clearly that this work on this slide is part of the PhD of a colleague and good friend of mine, Ted O'Reilly, who I've worked with for quite a long time. So I'll take some credit on this, but I have to give him a lot of the credit. So the next idea was to develop a system which could be applied to larger scales. Again, we wanted to have this passive aeration system. So in other words, allow air to get into the system without using mechanical components. Okay? So in this case, we decided to bring air to water, or water to air, rather than air to water. So if you remember the diffuser system I talked about before, we're trying to blow air into the water column. In this case, we were going to pump water around to enable air to get into the system itself. It's much easier to pump air or pump water than air for a variety of reasons. So we made some very good decisions along the way to cut costs, such as the introduction of various clever valving systems in the unit, and some very bad systems which we should have known as, from a structural point of view, where we tried to stack units on top of each other to cut costs. But yeah, structurally that just wasn't going to work. It turns out that water weighs a lot. So it does when you try and have thousands and thousands of litres stacked on top of each other. But this technology worked, and after Ted's PhD, we developed a commercial partnership with a company called Malloy Precast and also with Kingspan, and we started building these treatment systems at scale. If you live near in Kilmovee, this is the treatment system based on that technology which is treating your wastewater at the moment. Well, I assume it still is anyway. Mayo County Council are operating it and they haven't come back to us since. And in Moneygall, this system is, for example, a treatment system that we built in Moneygall, which is in County Offaly. And actually there's really interesting, when we were building that system, it was around the time of Barack Obama's visit to Ireland. And we had a lot of dealings to access the site with the security services, the US security services, the Gardaí at that time as well, because the whole place had to be shut down and manholes sweeping, etc., etc. So, in my career, I think this is the one. I'll talk about some technological success later on, but this is one that I feel got away because, and of course, I'm biased when I say this, but this technology really worked. It was extremely cheap. I haven't seen a wastewater treatment plant that operated as cheaply as these ones, met the discharge limits, and I'm unaware of any mechanical or maintenance problems since we installed these systems. Perhaps they're occurring and no one is telling us. But if we had some moderate commercial success with it, but probably not as much as I feel we could have. So technology with loads of different advantages. And one of the nice things about this technology as well was that it was the way we were aerating the system. It had never been modelled before. So we, with Noelle Jones, did a PhD. She now works in ATU, but she did a PhD on how to develop new biochemical and hydrological models to actually develop or to model this particular type of treatment technology. And we had really nice collaboration with Hydromantis, a Canadian company, as part of this software or this project, who I still collaborate with in wastewater modeling. While all that was going on, with my colleague Ted O'Reilly, we also built a research facility out in Tuam, and should obviously give huge credit as well to Michael Rogers, who was here for the start of working here at the start of this process. And this treatment facility is still out in Tuam, and basically it was a wastewater treatment plant designed to allow industry to test different and new technologies in wastewater treatments. Up until then, if you tried to test a new technology, there was a problem in Ireland because you had to basically sign off that your technology would not disrupt the existing treatment plant. We developed this research facility, which was not subject to any discharge limits, etc., because we were taking wastewater from a large facility and pumping it back into the same facility. So in that site, we tested maybe maybe 30, I can't remember, 30 or 40 different companies, various technologies, various devices, various sensors, a whole pile of raft of different suites. And we also used it as a demonstration site for our technologies we were developing ourselves. So it proved really successful. We also designed and built a remote monitoring unit that could be brought around to different treatment plants around the country to monitor in real time how those treatment plants were performing. Okay, so just a quick detour into some other areas of research for a couple of slides before we go back to this. So the area of aquaculture, to be honest, I don't know anything about fish or the biology of fish or the ecology of fish, etc. But in a way, if being cynical from an engineering point of view, an aquaculture facility is like a different type of wastewater or water treatment plant. Okay, instead of growing bacteria, you're growing fish, but a lot of the same principles apply. So we have, over a number of years, done quite a lot of research in the area of aquaculture, so trying to bring some of the technology that we developed for wastewater into the aquaculture field as well. Much of this research has been done in collaboration with various European partners, so most of it has been funded by the Interreg or Horizon Europe or Horizon 2020 over the years. And I suppose our key focus, as I said, is technology transfer from water and wastewater treatment into aquaculture. But in terms of our own research group, we also developed a lot of new, what are called life cycle assessment approaches. So these are different approaches to measure what are the environmental benefits or disbenefits of any particular process or system. And we first started applying some of these techniques, which are now being applied, to a variety of engineering and non-engineering applications in the area of aquaculture. Another area, a really nice project, which we coordinated here in the University of Galway. An EU project is funded under the FP7 program, so that was from 2014 to 2018. It was a project called Waternomics. And this came from a lot of the kind of work that a lot of our process control work, which I'll come to later on, relies on data from water infrastructure. So one of the ideas here was how to use the data that will be gathered from water networks to try and reduce water consumption, and also to improve the control and maintenance of water network systems. Okay, so these are the systems that bring water from the water treatment plant to your tap. The project also looked at a variety of different fault detection and diagnosis techniques. So these are techniques that allow us to use the data to determine whether there is a fault somewhere in the system. Remember, these systems combine thousands or tens, hundreds or thousands of kilometers of pipe networks, valves, pumps, sensors, a whole array of equipment that we don't see. And if any of these break down, it can cause inefficiencies in the system, but the system might keep operating. But it's not good when you have an inefficient system. And the project also developed a number of gamification aspects which would allow us to, I suppose, help end users, such as in schools, houses, or in airports, an airport in Milan, because that was one of our trial sites, Linate Airport. Thessaloniki in Greece was a city that we used as part of the trial, and then the project, and then we had trial sites here. So how do we get people to engage with water consumption and engage with water sustainability? So I see Louise Hannon here, so she might have nightmares about this project. So kind of taking some of what we learned there, we applied it to the energy sector, so through a project called Emerge. Again, that was a project we coordinated here. This project was really nice, really interesting one. Okay, not in the area of water, but we were trying to apply, as I said, some of those techniques to how energy is consumed in schools. So the project involved 13 schools across 6 countries. And I won't go into a lot of what we did, but it was a very interesting project that kind of combined data science, engineering, and social and behavioral sciences, and a lot of working with students during the project. Unfortunately, we did it at the worst possible time, because of all the places to work which are in COVID, schools were the worst, because they closed down. Of course, when your demonstration sites are schools, and all the schools across Europe closed down, and closed down for long periods of time, and even after they open up, they don't want anyone external coming next or near them. They also didn't want additional, I suppose, digital interaction for the students, because that was an alternative. We could have tried to do some of the work online with the students, which we did do, but of course they were getting all their lessons online, and the schools were telling us, look, you can't add more online stuff to this, it's challenging enough as it is. But in the end, actually, we got through it, and I think, given all the circumstances, probably the worst possible circumstances, came out with some really nice work. And there's some papers hopefully to be published on that later on this year, plus a PhD thesis, which will hopefully be finished this year with Raquel Lima. Some of the work we did, both in NERG and in waternomics, kind of led us to develop a number of different approaches in the area of fault detection for building water networks, including this building here. So again, can we create different data-based methodologies that can be applied to buildings, whether they're education buildings, industrial buildings, or city water networks, that would allow us better detect faults within those networks. One of the key things we did, which might surprise you, that was quite novel in this project, was we used real data, because I would say 99.9% of the papers that have been published to date had used simulated data for water consumption in buildings. But the problem with simulated data is that it's all correct. Whereas real data, sensors frequently break down, they give 0 values, they give minus flow values, they give flow values that are completely ridiculous, but you have to deal with all of that. And so this was part of this project was not just developing fault detection for the water network, it was actually detecting fault detection methodologies for the data itself to try and understand when the data you're getting is correct and when it might not be correct. So that project finished in 2022 and is kind of feeding into a lot of work we're doing at the moment. Okay, so yeah, unfortunately my clock here is kind of stopped and kept resetting so I'm not sure how I'm doing time anyway. So back to wastewater treatment and process control, back to this main theme. I spoke a little bit about aeration, maybe not so much about the process control side. So on the process control side, we have been and are continuing to develop a number of different ways to automate wastewater treatment systems. And the key thing in our previous research was to try and optimize 2 things. One is the energy consumption, or 3 things, sorry. 2 is the throughput capacity, so can we push more wastewater through the same facility? And 3, which is like the absolute essential, is meet regulatory limits, because of all the things a utility cannot afford to do, it's not meet the regulatory limits. So we developed 2 PhD projects, one being completed this year, which has been submitted, and one in 2018, and there are some other work in this area on the way. Developed a suite of tools and methodologies which we tested in large and real wastewater treatment plants, which allow you to optimize these 3 approaches. And in Shane's particular thesis, when we applied these methodologies to a number of small to medium-sized treatment plants, the energy savings were between 34 and 50%, so enormous energy savings, while still meeting regulatory limits. So moving on to, I suppose, Vortec. Leisha mentioned it in the introduction. So this has been the most successful commercial venture that we have had to date. So again, it goes back to this whole thing of aeration. Can we develop a way of aerating in wastewater treatment that would be passive or not force air into water? So we developed a vortex-based system, and I don't know why this is not playing, because it was earlier on automatically. Anyway, there should be a nice video there playing to show how the system works, but it's not coming up automatically, so apologies. So we developed a kind of a system which will basically extract wastewater from the treatment system, pump it through, I suppose, just a cylindrical shaped object. We don't actually give out drawings as to the shape of the object because the packing could easily be broken then. And what happens is that we ascertain a certain velocity, water and fluid velocity in the system, which creates a vortex in the center of the system and sucks air down through the system. And what you get is this highly aerated mixture of air and water, which is driven, okay, it's pumped up here, circulated here at high speed, and driven down into the wastewater treatment tank. So that's the mechanism by which we create aeration, but we also can create mixing at the same time. It's quite a complex fluid dynamics principle to get it right geometrically, but it's actually a very simple application. You just need one pump and a nice looking system like that. It allows us to control aeration and mixing. One of the problems with existing aeration technologies is they're not easy to kind of control. You can't easily turn up the aeration and turn it back down again or stop it. And when you're stopping it, for example, you might not be able to mix at the same time, which is very important. This technology allows us to do all those things, and it's also very low maintenance. I should acknowledge a lot of the fundamental fluid dynamics work was carried out as part of a PhD of Sean Mulligan, and that was in TUS in Sligo. Enterprise Ireland funded this project, and I have to give a lot of credit as well to Paul Butler from Enterprise Ireland, who really helped us both in getting the funding to drive this forward and giving us a lot of commercial advice along the way. So the system in practice, because Vortec is now a company, it's based in Galway, but selling technologies across different countries. So the system in practice looks like this. So these are large-scale units when they're applied in practice. They're up to 4 meters in diameter, and the only limitation on their size is actually logistical issues such as shipping and trucking issues, which is limiting us. And our first, I suppose, supporters were Irish companies that allowed us to demonstrate the technology, Warden Burke and ABP. And so the company is, I suppose, expanding at the moment, and we currently have signed a big contract in Australia to provide technology to utility over there, plus hopefully others in the pipeline, so it's quite exciting. Another really exciting project in the area of air entrainment and infrastructure was you can actually see both the last unit and this particular system I'm going to describe in our engineering laboratories here. So you may or may not know that London's sewer system is very old, and over the last number of years they've been constructing a new sewer system. Prior to the construction of the sewer system, about 18 million metres cubed of untreated sewage was going into the Thames every year. I still probably wouldn't swim in there, but it's probably better than it was before. One particular area that was of concern was an area in London called Putney Bridge. And there's an old historic bridge there that underneath had these what are called CSOs. So these are overflow places where sewage can overflow into the river. And they wanted to capture this overflow, but they had to do it without touching the bridge, because the bridge is historically designated. Okay. The problem was that the existing solution, which had been proposed by, I won't name the international engineering companies, wouldn't have worked. It couldn't be built without doing damage to the bridge. Warden Burke, which is a local company here in Kilcolgan, a construction company, had an idea as to how it might be done differently, but they had to demonstrate that would it work, would their solution work. So they came to us to develop both computational models of it, but also a scale model of it, so that we could test whether their solution would work and make any changes that would be necessary for it. A big design challenge, which resulted in us making a lot of changes, was an issue of air and gas pressure. So in sewer systems, we cannot allow air and gas pressure to build up in the system, because it can cause what you might see geysering from the sewer systems. And this was a particular challenge at this location. So we built a 15-meter long scale model, and the design of that scale model, I'd say, is one of the most complex engineering things we've done, because it had to be precise. In order to replicate what would happen on site, the scale that we designed this at had to be very accurately done. And we basically developed a new way of intercepting the wastewater underneath the bridge that would allow Warden Burke to tunnel towards the bridge instead of having to dig around the bridge, which they did do, and we were able to demonstrate that the solution would work. And it was quite nerve-wracking, because we had international design teams from some of the biggest engineering companies in the world coming over to test our solution and see that it actually did work. So that was a really fantastic project. There's a video here which I'm not going to let it all play. But this is the system in the lab, and this is the system being built. What you see here is what's called a tunnel boring machine, which is boring the main tunnel. And at the end near Putney Bridge, they have a lot of, I suppose, created aesthetically pleasing public areas to kind of hide a lot of the work that was done in this project. Okay, just a brief, I suppose, detour. Other work that we've done has been in the area of wastewater disinfection, which is an area of great interest to me. Killing pathogens and bacteria in wastewater and water is actually essential, as I'm sure everyone realises, but it's actually very difficult. And Kelly Fitzhenry carried out a really challenging PhD in the area of wastewater and water disinfection, using what's called post-UV technology. One of the other ideas we had was a treatment technology that would capture gases produced during wastewater and treat them in the same technology as would treat the wastewater. My first PhD graduate was Paul Ford, and he did his PhD in this. It actually worked brilliantly. The problem was that when we built it and tried it on site, and we tried to engineer this very carefully, after about a year, due to applying suction pressures on and off, the whole thing collapsed like a can of Coke. We came outside one day and our whole system had collapsed. When we redesigned it to, I suppose, have a 20-25 year lifespan, the costs were just too great, so the technology was never viable. But it was a really nice PhD project. And yeah, that's what engineering is about. You make mistakes. Other areas of work we've carried out are in the area of sand filtration for water and wastewater treatment. Really simple technology. I've collaborated a lot with colleagues in microbiology just to understand the mechanisms by which we can remove various contaminants using sand filtration. And also done some work in the geotechnics with colleagues of mine, Brian McCabe and Jamie Goggins. So we're getting close to the end now, for those who might be getting bored. Probably one of the nicest projects worked on over the years is a project called Inaqua. This was a sanitation-based project, which is using, believe it or not, worm-based sanitation. So treatment technologies that leverage worms to actually remove wastewater. There was other technologies that were used as part of this project, but I'm not going to go into those. This was funded by Horizon 2020, and it was led by Novatech, and myself and my colleagues Louise, Alex, and James worked on this project. So we were kind of technical directors of the entire project, which was quite complex because there was demonstration sites across the world, from Tanzania to India, Turkey, Romania, France, Spain, Peru, Ecuador, Scotland, and Ireland. I think that's all of them. So a lot of moving parts in this particular project. And the idea was to introduce this technology plus other technologies and demonstrate them in various locations around the world to see how they would work in different climates, how they would work particularly in areas where you don't have access to electricity, flushing toilets and various things like that. So it was a very nice and complex project. I could do hours talking about this particular project. During that project, one of the places we visited was in India, Bengaluru, a small little village near there with a population of 30,000, but that's a village in India. We visited was a place called Devanahalli, where I probably saw the most brilliantly engineered treatment plant I've seen anywhere in the world. So this was a treatment plant treating what's called fecal sludge. So basically they can't afford to flush toilets over there. They can't waste water by flushing it down the toilet. So they do their business. It's collected in what are something equivalent to septic tanks and brought to a treatment system. The idea here was, how do you design and build a treatment system that does not use electricity, has no pumps, and just uses hydraulic pressure to move this matter all around the treatment plant? And they did it. This is not something we did, this is something we saw over there. So basically you get wastewater in, out, you get compost and water that's suitable for irrigation. A really fantastic treatment plant. And the only problem in India is the scale of the problem is just so vast, but they actually in some locations have some of the most amazing solutions because they have to. And some of the, one of the engineers was telling us that some of the outputs from the installation of that treatment plant was in that town, after the implementation, child malnutrition was almost eliminated, because the malnutrition there was not due to lack of food, it was due to diarrhea, due to poor wastewater. School attendance increased, you've got reduced poverty, reduced disease, economic opportunities, etc. So it was a fantastic opportunity, or project. An area that I think is really exciting that we're working on at the moment is in the area of climate change and wastewater infrastructure. So one of the big things that's going to impact our storm networks and our sewer networks into the future is going to be rainfall patterns. And we're developing, and I think we are the first people to do this for wastewater influent, models that will enable us to link climate change predictions to how they will impact our sewer networks, and particularly our wastewater treatment plant influent volumes into the future. So I won't go into any details on that, but that's exciting work which we have published on, and there will be more to come. Okay, so the last thing then is in the area of cycling. I also do some research in the area of cycling. Oh, the videos are now working, great. So we were lucky enough to live in the Netherlands in 2023, and this is what cycling looks like in the Netherlands. You don't have to dress up as if you're going to battle. You just go out and cycle your bike, because everyone just gets in their bike over there. Secondary schools have hundreds of bikes. Kids are never brought to school by car. It doesn't matter if it's snowing, raining, storm, whatever, they all cycle. And actually the thing I remember most from our stay in Eindhoven is seeing the gangs of teenagers, like 50 or 60 teenagers cycling together to school in the morning and home in the evening. So it's just fantastic. So we do some research in the area of cycling. Ireland has a transport problem, I think everyone knows that. I have a particular focus on cycling and public transport when it comes to teaching. And some of the projects we've done there are in the area of greenway design. So these are, you're probably all familiar with the Great Western Greenway, and there's greenways now in Limerick and Waterford and various places. So we've done a lot of work on how these should be properly designed. How do you go about the route selection of these greenways? What are the kind of safety concerns that cyclists have in relation to both greenway design and other cycling network design, and how they can impact emissions, how the building of these greenways and cycling networks can impact emissions. Transport being one of our most challenging areas when it comes to emissions. Other areas that we look at are the emissions. So I've led the calculation over the last number of years. The university is obliged to report what's called Scope 3 emissions. Amongst those are the emissions resulting from people commuting to campus. And so in our group, we have calculated those emissions from the start of them being calculated. And currently that's now we're handing that over now to the Director of Sustainability, who's a former PhD student of mine, Richard Manton. Really nice master's project at the moment in the area of pavement design for greenways. So how can we actually design the pavement structure to make cycle networks and greenways much more comfortable? Might sound quite simple, but it's actually a really interesting project. And I collaborated with some colleagues in the School of Business and Economics on the types of impacts that remote working could have on emissions and other economic factors. So actually I'm hopeful that work will come out later on this year. One of my favourite projects is in the aerodynamics. I know a lot about cycling, didn't know much about aerodynamics before we started this project, but we were lucky enough to form a collaboration with the Technical University of Eindhoven and Professor Bert Blocken in Eindhoven. So this project involved myself, Bert, Magda, and Thomas Andrien from the University of Liège. And we were the first people to look at the aerodynamics of Paralympic cyclists, which you may think was so what. But it's actually really, really technically challenging from an engineering point of view. And, I suppose non-Paralympic athletes over the years have had so much scientific sports science applied to them. Our idea was, why not apply this to Paralympic athletes? And a lot of techniques that were used to model the aerodynamics of cyclists, Paralympic cyclists, were just taken from non-Paralympic cyclists and applied to them. But we found for various types of bicycles, these rules did not apply at all. This project resulted in 8 papers during one PhD, which was pretty astonishing. And it was just a really cool area of work. There was both wind tunnel testing, computational fluid dynamics testing, and some really nice, collaborations with different partners across Europe. And then finally, obviously, you have to apply some of these in real life. And I spent a bit of time cycling myself, including in Rio. And where aerodynamics comes into play is when you're trying to go for medals in World Championships or Olympics or Paralympics, the difference between first and fourth could be 0.4 of a second. So, if the seam on your jersey is out of place, that could lose you a medal. Literally could be that. And so there's a lot of nice memories from Rio. One of the memories I have is of the security in Rio, how, I suppose, overwhelming it was. They literally had, it seemed like, the entire army there, and yet how friendly it was. Before we went to Rio, we were training in a place called Uberlandia, which is near Sao Paulo. And the police were a bit concerned for our safety there, so we had police escorts all around the place there, which meant we could go as fast as we wanted, basically, because they kept the traffic away from us. And it was just a really, really kind of fantastic, and it was nice to actually link some of the research that I was doing and actually put it into practice myself. Got really nice opportunity. This is a photo from Rio, cycling in Rio, and lots of other countries. Probably my favourite venue ever was in Izu in Japan, and you can see in the background about 150 kilometers away, Mount Fuji. So really great memories of racing over there. And luckily enough, we got to meet the president afterwards, and the president's dogs, that's Sophia, up there. She's not looking. There she is. Little Mark said I wasn't born at the time. Okay, so where to next? So we're at the moment where, I suppose, one of our key areas of focus is we've looked at energy recovery, as I mentioned before, discharge compliance. A big area that utilities are going to come under pressure in the area of wastewater treatment is in process emissions. So what we're now trying to do in our process control applications is ensure that we not just treat the wastewater as well as we can, that we meet discharge limits, that we reduce energy consumption, but we also have to reduce the emissions coming from the treatment system. And these three things are often pulling against each other. We have a lot of other work, particularly I think in the area of climate change and infrastructure risk, which I think will be important. I won't go into this, and I'm just going to say thanks to everyone. Okay, and that's from our side because we didn't get a photo.